Welcome to another seminar for structural engineers, and this time we're on SpaceGass for Dummies Part 4. And remember, the dummy is me. I'm still trying to get my head around SpaceGass, and here we've got to Part 4 already, and I'm here to share my learnings with you. So in Part 3 we took a two-dimensional image and imported it into SpaceGass and used it as the cross-section of a prismatic member, and so joined several together to form this roof sheet. Now we're going one step further. We're going to use plates, and plates in SpaceGass are basically finite elements, and they're finite elements connected via nodes. Generally they're either triangular or they're quadrilaterals, and so you either need 3 nodes or 4 nodes, and the mesh size that you choose will give you different results. So it's important to consider the mesh size when considering finite element analysis. There are many other videos you can go and watch on what is the optimum mesh size. So we took the basic profile shape, and with that we turned it into nodes. So here are the nodes. If I zoom in, on the profile, you'll notice we have this shape from our imported image, and at each change in direction we put a node. So that gave us a series of nodes in one plane. We then copied them over and over to produce a 3-dimensional structure with 2-dimensional plates in both directions. So what have we ended up with? If I turn the nodes off, we've ended up here with the analysis results. And what am I showing? So the legend is the von Mises stresses. Now, when you're giving plate results, von Mises is most commonly referred to, and it's simply a way of combining direct stresses with shear stresses using a formula developed by the man von Mises. And there are other options, and again there are other videos to describe the differences between the way of summating direct and shear stresses to get your overall stress, the stress that you need to be looking at. In analysis results, you can pick from a whole range of stresses, either direct stress in Y or X, shear stresses, principal stresses, and so on, and even shear stresses. So if I select the XY shear stress, it redraws it, and on the right hand side the legend now shows you the range from 21 MPa to minus 32 MPa. So it doesn't look like the shear stresses are a big deal for this particular one. The design criteria is probably going to be governed by the van Mises stresses. So this is the end product, and to have a look at the deflected shape, click on the little show displacement icon on the left hand side. And so now that shows the deflected shape, but it's not always that clear. So what we can do is turn off the structure by toggling between show plates and not show plates. We can take our edges off. So now we have the deformed shape with the von Mises stresses attached. If you want to exaggerate the displacements, hold down the D button and use your scrolling mouse to change the shape of the deflection. As usual, you can rotate around by holding down your left mouse button. You can scroll in and out using your scrolling mouse, and if you want to pan, it's your right mouse button. Okay, so that's the end result. We've already modeled it, we've loaded it, we've analyzed it, and now here's the end result. So how did we get there? So I'm showing you the end of the book before I've started the beginning of the book. So let's switch off the results and switch off the stresses, and you're left with a blank sheet of paper. Oh gosh. So let's show the plates, and one of the things you can do is show the edges of the plates, and there's a little button here marked show the gaps. So if you switch it off, your plates all merge into one. But this is quite a useful tool as to allowing you to distinguish between the different plates. And as you see, they're all pretty much grey. And if you select one of these plates and click on the properties section, you'll see I've picked the plate theory of Kirchhoff, which is thin plate theory. The alternative is middling, which is for thick plate theory. So basically the Kirchhoff is going to ignore the through depth shear properties. And you can put in the real values for this plate. It's 0.55 millimeters thick, and I'm taking that as its membrane bending and shear thicknesses. The material we're using is steel, and so the usual steel properties come through here. Now, interestingly, it says my node AB is node 4600, and node B is 19,709, which means we've got a lot of nodes. So we show the nodes. There we are. Our little element here is bounded by these nodes. Now, this will give a warning, at least, when you come to analyze it. One of the things it doesn't like is plates which are twice as long, more than twice as long as they are wide. So if you hover over with your mouse on one of these plates, it gives you a summary of the properties of that plate. So the type, it's a thin plate using Kirchhoff theory, and the thickness is 0.55. It tells you which the nodes are. Down at the bottom it tells you the size. Down at the bottom it tells you the size in meters. So the actual AB dimension is a mere 7.6 millimeters. The BC is 25 millimeters. CD is 7.6 millimeters, and so on. So these are relatively small plates, and remember, the smaller the plate, you can get more accurate results, but you can get higher and higher stress concentrations, which may not be realistic. So you have to take the results of finite element analysis with a pinch of salt, because what most FEA packages don't really do is look at tearing, or they don't look at stress redistribution. If anybody knows how I can get stress redistribution post-yield behavior in SpaceGass, leave me a comment in the description. So we're loading the roof up as we normally do. So we've got our self-weight, we've got our dead load, and that's applied as plate loads. So you select it. We've selected the whole lot to load it properly. And to find out what they are, you can click on the database button, and the data sheets that show your member pressure loads, or your plate pressure loads. Here we are. That fires up. I pull that in, you can see all the plates have numbers, and for this load case 2, we've got a Y pressure of 0.1 kPa. It's minus because it's in the opposite direction, in the Y direction, so downwards. And you can scroll through that and look at other load cases. So we've already loaded it. We can apply to all plates by selecting all plates and applying the pressure loads. And so up here we've got our draw nodes, draw members. Here we've got our draw triangular plates and draw quadrilateral plates, should you wish. You can also add plate cuts and plate strips, which gets even more complicated if you want to divide the plate up. And we'll keep things simple. So you can select one or more plates and then load, or a number of plates, and load it using the loading tools at the top of your screen. Click on the plate pressure load. You can select the load case and then apply to the selected plates individually. And if you click OK to that, you'll probably want to get the size for all of these plates, and you add an X pressure or a Y pressure or a Z pressure. Because we're going down, you'd add the numbers in here. So you can do 1 kPa to each of these should you see fit, but we'll cancel that. So let's abandon that change. More likely you are going to be wanting to apply the loads as a selected group. By default that's not selected, which is a bit silly. So if we pick that load case, click OK, then we've only got one table to fill in, which makes a lot more sense. Let's say we'll cancel that because we've already loaded it. So zoom out. So we've got our dead load done, we've got our live load done, we've already got our wind up load done. We've installed 2 ultimate load cases, so that's gravity load factored downwards, and then we've got wind uplift counted by factored gravity load. Okay, so as usual you click on the analyze and we'll do a linear static analysis for that. By default it picks all your load cases. By default it picks linear. You could also do a non-linear. You're given the type of plates that you're looking at, whether you're using a Paradise or a wavefront solver. Experimenting with this, I don't see a great deal of difference between the results I get. So let's click OK, and it will throw up a warning. It says your ratio exceeds 4:1. Do you want to ignore it and continue? I'll say yes, and off you go. Linear static analysis runs, and it does several iterations until it converges with a result. Okay, so it's done it all, and you click OK. So let's zoom out. We don't want to see our loading. So what do we want to see? Well, we're more interested in the analysis results, so let's have a look at because it's plates, you're really interested in stresses. So let's have the analysis results, and as we said, von Mises stresses. Okay, and it draws a pretty picture there. Lots of colours, going from hardly any stress at all through to 450 MPa under the combination of wind and downward dead load. Similarly, you can switch on the deflection as we've seen before. If we zoom out, we can say yes, it's bending in the upward direction, and the centre parts, which are less stiff than the ribs, are obviously deflecting more. Now you can switch on the numbers, but your numbers get rather illegible, as you can see. So that's one of the troubles with the plates. Okay, so how did we build it all up? As I said, let's get rid of that. Let's get rid of that, and let's get rid of that. So now we've just got the bare sheet with its plates. One of the beauties of SpaceGass is it allows you to copy in a line, and to the extreme where you can copy the whole thing and move it again. So if I select, drag and select plates, and then we can copy along a line. I only want one copy. You can do multiple copies. And I click OK. Let's pick a point here. And I'm going to move it to there, and it will immediately extend. So it's now twice the length and twice as many nodes. Have we got supports? Let's have a look at the supports. To see the supports, you need to show the nodes. So it's copied over the supports on the end, which is quite clever. It's copied over all the properties and all the plates and all the nodes. And if you want to see the gaps between the nodes, there you go. So that's the basics of plates. You can start doing a more basic mesh by using the mesh tools. So if you right mouse click on any of your plates, you can mesh them, and so the usual one is to use the basic one. So it's looking for subdivisions. So split it into triangles or squares, and how you would do it. Make split plates into parts no more than, well, by default they wanted the plates to be 1 meter, and we're getting way lower than that. So if I say effectively 2 millimeters, which is a very small mesh, and let's see if it does it. Yes, it breaks it up. But now something else it doesn't like. You've got all these nodes that are now not connected to the plate. So this plate is now going from that node to that node, when really we need to break that plate up as well. So you could go on and on subdividing and subdividing, but there comes a point when the smaller your mesh, the less useful your results become. So remember the adage that all models are wrong, but some of them are useful. So that, in a nutshell, is plates in SpaceGass, and enjoy the rest.